All right, let's take a look at this question. 16.9, predict the products for each of the following reactions. In each case, determine which product is going to predominate. So we'll start with the first one. And I'm just going to draw a line here to, there we go. All right, so we've got HBr and we're at 40 degrees Celsius. So these would be thermodynamic conditions. And when we're running thermodynamic conditions, the 1,4 adduct should be the major product. So we'll put 1,4 should be the major product. Just to make some room, maybe I'll just move that over. Oops, didn't mean to do that. Yeah, we'll move this. There we go. We'll put it up here. Okay, so let's start by drawing the curved arrow to form the allylic carbocation. We're going to draw the proton transfer like this. And if you did it, if you did the proton transfer down here, either way, you would end up with the exact same answer. So I'm just going to do it here. And then we're going to end up with a carbocation, which is going to look like this. So we have this tertiary carbocation that is resonance stabilized. So this is the resonance, the curved arrow that shows the flow of electrons, or the delocalization of the electrons, I should say. And then we end up with this, and then we have a carbocation here. So those are our two carbocations. I'm going to erase this arrow that represents the movement of the electrons, or the resonance hybrid in the resonance hybrid. And now we're going to show the nucleophilic attack by the bromide. So here's my bromide here. Here's the bromide here. So I get a nucleophilic attack here, and I've got a nucleophilic attack down here. And that gives us two different products. So I'll draw this one like this. So I've got my double bond here, and then I'll have my bromine here like this. And this is going to be racemic, since this is a chiral compound. And then the other one, I'm going to need a little more room to draw that one. So it's going to look like this, like that. And this is also racemic. This is also racemic. And the major product is going to be this one. This is the 1,4 adduct. So this is the major product. Why? Because if you count the carbons in the molecule, 1, 2, 3, 4. Here we have the proton added at carbon 1 and the bromine added at carbon 4. So this is the major product. All right, give me a thumbs up if you got that one. Or if you have a question, stop me. All right, good. Okay, great. Let's try the next one. We'll go a little faster this time. So we've got our HCl molecule. We're at 0 degrees Celsius, so the 1,2 adduct should predominate since these are kinetic conditions. So let's draw the formation of the allylic carbocation. We're going to draw the curved arrow, and we end up with this carbocation. Then we're going to draw the other resonance contributor. And let's draw that. Oops, it looks like this. There we go. And there's our carbocation, like that. Then we draw the chloride. I'm going to remove this arrow just because I don't like having more than one curved arrow on something. We have this nucleophilic attack. Oops. Let's spruce this one up. And this nucleophilic attack like this. So we end up with this compound. And this is racemic. And then we end up with this compound. There you go, which is also racemic. But this one is going to be the major product. This is the major because it is the product of the 1,2 addition, right? If you number your carbons, one, come on. There we go, 1, 2. There you go. So it's the product of 1,2 addition. And there you have it. We've looked at the formation of some products using thermodynamic conditions and kinetic conditions. So remember the first one, the first example, 40 degrees Celsius, these are thermodynamic conditions. And then here we looked at kinetic conditions. And in thermodynamic conditions, 1,4 is going to predominate, and in kinetic conditions, 1,2 is going to predominate. There you have it. Well, with that, let's move on to section 16.6, which is an introduction to pericyclic reactions. We don't look at all the different types of pericyclic reactions in Chemistry 3111. However, they are all covered in the textbook. So if you want to take the time to be exhaustive and to read all of the chapter, even the sections that we're not going to necessarily cover, feel free to do that. But up till now, every reaction that we've looked at has either been has usually been an ionic mechanism, and then some free radical mechanisms as well. But pericyclic reactions occur without any ionic or any free radical intermediate. So there's three main types of pericyclic reactions. You can imagine that next we're going to look at what the three types are. So three main types of pericyclic reactions. The first one is a cycloaddition reaction, and the Diels-Alder reaction, that's the name of a reaction, is going to fall under this umbrella, and that's the one that we're going to talk about in Chemistry 3111. The next one is an electrocyclic reaction. Again, we're not going to cover electrocyclic reactions in our class, but they are important reactions if you want to take the time to look at those. And then the last one is a sigmatropic rearrangement if you want to take the time to look at those. Now, the difference between those and other types of mechanisms that we've looked at is that these reactions, the sigmatropic rearrangement, here the pericyclic reaction, or sorry, the electrocyclic reaction and the cycloaddition reaction, what they all have in common is that their reaction mechanisms are concerted. If you go back and look at the curved arrows, they all occur at the same time without any intermediates, right? The mechanism is just a ring of electrons moving around a closed loop. The transition state is cyclic, and you're going to see that as we move on in the content. And the polarity of the solvent, whether it's polar or nonpolar, has very little effect on the reaction rate. It doesn't change the transition state, or doesn't have an effect in the transition state, rather, because the transition state has little, if any, charge whatsoever. Well, if you take a look at a summary of the cycloaddition versus electrocyclic versus sigmatropic rearrangements, we see changes in the number of sigma bonds for cycloadditions and electrocyclic reactions. There's no change in the number of sigma or pi bonds with sigmatropic rearrangements, but in a cycloaddition reaction, we also lose 2 pi bonds, and in an electrocyclic reaction, we lose 1 pi bond. Again, the area of interest in Chemistry 3111 is going to be the cycloaddition reaction. Now, the type of cycloaddition reaction we're interested in is called a Diels-Alder reaction. Diels-Alder reactions are very, very useful reactions. We also call them 4+2 cycloadditions because we start out with a diene, right? That's where we started this chapter, was talking about conjugated and cumulated and isolated dienes. So you have a conjugated diene, you call that the diene, and then you have something that has a pi bond in it, and you call that a dienophile. So a dienophile, and that is something that is seeking a diene. Now, why do we call it 4+2? Because in the diene, we have a total of 4 atoms involved in the reaction. And in the dienophile, we have a total of 2 atoms that are, again, involved in the reaction. Now, if you draw the curved arrow mechanism for this reaction, you can draw it the way that it's shown here. You can see that all the arrows are going in a clockwise fashion. But I'm going to show you that you could draw the curved arrows in a counterclockwise fashion, going backwards, counterclockwise, and counterclockwise like this. So it doesn't matter if you draw the arrows clockwise or counterclockwise, you end up with the same product no matter what, and you end up making a cyclohexene molecule. So you end up with 1 pi bond overall in the final product. So if we look at the potential energy versus the reaction coordinate, we start out with the diene and the dienophile. We pass through the transition state, right, which was cyclic, and you can practice drawing the curved arrows. You can, again, draw them clockwise like this, okay? Or you can draw them counterclockwise. Let me fix that last arrow to show that we're forming a pi bond there. But you see that it's an exothermic reaction, isn't it? Right? We end up making something that is more stable in the end. Now, something that's interesting about Diels-Alder reactions is that since the product is more stable, they are thermodynamically favored at low to moderate temperatures. But what's really interesting, though, is that if you crank up the temperature really high, you might think, well, then the reaction is just going to go even faster. But in fact, it doesn't. What happens with the Diels-Alder reaction, and you need to know this, is that when you get to a temperature above 200 degrees Celsius, what you actually do is the reverse. So if you turn up the temperature too high and you try to rush the reaction, it just goes backwards and you end up with nothing. You just go right back to your starting materials. Now you might be thinking, now why the heck would it do that? Well, the reason why is because when we're determining or evaluating the spontaneity of a reaction, what do we have to consider? When we're talking about spontaneity, we're talking about the change in Gibbs free energy. We have to consider both the enthalpy and the entropy, right? Because delta G is equal to delta H minus T delta S, right? Going back to general chemistry 2. Now, if you're like, jeepers, I don't remember my general chemistry 2 that well, Mr. Dion. Well, I got some good news for you. I can explain it to you so that this will make complete sense. Okay? So first, let's talk about the enthalpy term, delta H. I already told you, I mentioned a couple slides ago that this is an exothermic reaction. Remember in organic chemistry 1 when we calculated delta H's for reactions and we looked at bond dissociation energies, right? Bonds broken minus bonds formed. Well, since we end up breaking a total of 2 pi bonds, right? We break 3, but we end up gaining, 2 sigmas in a pi. So overall, we're technically breaking 2, and then we're gaining 2 sigma bonds. Well, since sigma bonds are more stable or stronger than pi bonds, that means that overall, the delta H term is going to be negative, right? It's an exothermic reaction. This is a negative number. Your delta H is negative. But not only do you have to consider the enthalpy term, you also have to consider the entropy term, delta S. Now, if I think about the change in delta S, I'm going from 2 molecules, right, to 1 molecule, right? 2 things to 1 thing. Well, hopefully you understand that 2 things are more disordered than 1 thing. So what's happening to the disorder? It's decreasing. So that means my delta S number is going to be a negative number. So I know that my enthalpy value is negative, and I have negative T times a negative entropy term. So that means that overall I've got a negative number here, and I'm adding a positive number here. Now, in order for my reaction to be spontaneous, my delta G has to be negative. So if this is negative and I'm adding something positive to it, when will this number be negative? It's only going to be negative when this is small, right? When this term is small. How is that term going to be small? When my temperature is low. Think about it. If you jack this temperature up super duper high, right? Then this term becomes too big, and then you take a negative number and you're adding something really big to it, and you end up with a positive number, and then it becomes non-spontaneous. If you really need the hammer and tongs approach, okay, if you think about negatives and positives, let's say you just do an example. Let's say you have negative 2, and then you add plus 1 to it. What do you end up with? You still end up with a negative number, right? But what if you have negative 2 and you add positive 3 to it? Then you end up with positive 1, right? You end up with a positive value, so you'd have a non-spontaneous reaction. So again, you want to keep the temperature low to keep this overall term as small as you possibly can. And that is how we control the reaction. So it says here, at very high temperatures, the entropy term, which is all of this, opposes the formation of the product, and you get the retro Diels-Alder, right? What was the retro Diels-Alder? It was just going backwards, right? Forwards, we call that the Diels-Alder reaction, but when you go backwards, we call it the retro Diels-Alder, and that occurs at really high temperatures, greater than 200 degrees Celsius, and the Diels-Alder will occur at high temperatures, but less than 200 degrees Celsius. All right, so retro Diels-Alder and Diels-Alder. All right, now I already told you what a diene and a dienophile is, right? The diene has the 2 double bonds and they're conjugated. But it says here that the dienophile, okay, needs to possess an electron withdrawing group or the reaction is going to require a really high temperature, which doesn't favor the product formation. So if you just take 1,3-butadiene and ethylene and you heat them up, you can form some cyclohexene, but it's really low yielding. It's not a very useful reaction. 20% yield doesn't sound like a day at the beach or anything, right? So how do you get the reaction to work in a higher yield? If you have an electron withdrawing group, which we sometimes call an EWG, electron withdrawing group, attached to the dienophile, the reaction is generally going to be spontaneous. So you don't even have to heat it up. It's just going to happen. So what's an electron withdrawing group? A carbonyl is electron withdrawing, right? There's a dipole going this way. Why? Because oxygen is more electronegative than carbon. Oxygen is the second most electronegative element in the periodic table. So again, when I have that electron withdrawing group on my diene, right, and this is the electron withdrawing group, the reaction is spontaneous. Now, what are some other electron withdrawing groups that I could use? I could use a ketone. I could use an ester. I could use a carboxylic acid. And what do they all have in common? They all have a carbonyl directly attached to the double bond, the carbon-carbon double bond. I could also use a nitrile, right? Remember, this functional group is called a nitrile because it is also electron withdrawing, right? You could draw the dipole here, you could draw a dipole here, you could draw a dipole here, but in the nitrile, you can also draw a dipole. Now, in terms of the stereospecificity of Diels-Alder reactions, it depends on whether you use an E or a Z dienophile. And again, you could call it a cis or a trans dienophile, depending on the dienophile. But if it's Z, if both of the groups on the dienophile are on the same side of the double bond, so you could call it cis or you could call it Z, it doesn't matter, then you end up with both of those groups being cis on the ring, on the six-membered ring that's formed. If they're trans to each other, or E, you end up with them being trans to each other on the ring. And of course, you'd end up with the enantiomer in this case because it could add both ways. And then an alkyne can also function as a dienophile, right? And you could practice drawing your curved arrows here, right? But I'm only breaking one of the pi bonds in this triple bond here. So we end up with a 1,4 cyclohexadiene. Okay, this would be a 1,4 cyclohexadiene here. Now, remember that earlier today we talked about how 1,3-butadiene and many other dienes can exist in the S-cis and the S-trans conformation because there's free rotation around this carbon-carbon bond. But the thing is that those Diels-Alder reactions that we looked at, they can only occur when the diene is in the S-cis conformation. You will not get a Diels-Alder reaction occurring between a dienophile and a diene that's in the S-trans conformation. Why? Because this carbon, this methylene here, this pi bond is too far away for the reaction mechanism to occur. It just doesn't happen. So let's say you have a molecule where the conjugated diene or the diene is locked in an S-trans conformation like this. You get no reaction, right? You can see how it's locked. What I have highlighted there is just stuck in the S-trans conformation. There's no rotation around this carbon-carbon bond because of the ring, and so you get nothing happening. Now, conversely, what if you had the diene just stuck in the S-cis conformation like in cyclopentadiene, right? Here you have the double bonds. Oops. You have the double bonds. They're stuck in the S-cis conformation. Well, then the reaction just goes like crazy, okay? It reacts very quickly. Now, when you're drawing the curved arrows, you're going to form a bond between this carbon in here, right? And that's this bond right here. Sorry, no. That's this bond here that was formed. Then you're going to break that pi bond and you're going to form a new bond here. That's this bond right here. And then you end up forming the pi bond, which is shown down here, right? Remember, you break a total of 3 pi bonds, and you end up forming 1 pi bond and 2 sigma bonds, right, overall. Okay, and you end up forming a bicyclic compound, which is pretty interesting, right? Remember bicyclic compounds? We even learned how to name those in Organic Chemistry 1. Now, cyclopentadiene, since it's stuck in the S-cis conformation, it's kind of an interesting molecule. If you want to do a reaction with it, if you try to store it in a bottle at room temperature, it will just react with itself, and it forms this molecule, dicyclopentadiene. So it's really even difficult to store this molecule. It's very difficult to store it. It can be stored, or you can probably crank it up really high, do the retro Diels-Alder, and then re-isolate the product. You know, that's probably an option. And you could draw the curved arrows for the retro Diels-Alder. You could practice them like this. Okay, so those are the retro Diels-Alder arrows like that. All right. So when bicyclic systems form, we use the term endo and exo to describe the functional group positioning. So we have two aldehydes, right? There's one here on this dienophile, and they can react in such a way to form the bicyclic molecule. And again, you can always practice drawing your curved arrows for the Diels-Alder reaction like this. But it can react in such a way that both of those aldehydes are pointing down and the protons are pointing up like this, or you can have both of the aldehydes pointing up and the protons pointing down like this. Now, since this, if we compare those two molecules, you have a 2-carbon bridge and you have a 1-carbon bridge. Now, since the 1-carbon bridge is smaller than the 2-carbon bridge, you might think, well, these big groups, these two aldehydes, it's going to be better to have them here, because when they're down here, there's going to be, you know, steric interaction because that bridge is bigger. But in fact, it's not the case. Okay. The major product is the endo product. This is the major product. And the reason why it's the major product is based on something called the Endo Rule. So the Endo Rule. So the endo position is the position that is syn to the bigger bridge, and the exo position is the position that is anti or away from the bigger bridge. So why do we get the endo product as the only product, or oftentimes the major product? Well, the reason why is nothing more than this, okay? It's because when you get the transition state, or when the transition state forms, there's a favorable interaction between the forming pi bonds, so the new pi bond that's being formed, and the pi bonds on the electron withdrawing substituent. So it says it right here. There's a favorable interaction between the developing pi bond and the electron withdrawing substituents. I think it's between the p orbitals that are on here, you know, and the new double bond that's forming. So again, even though it's not intuitive, that is the reason why we get the endo product. When you draw the transition state that leads to the exo product, you don't get that favorable interaction, okay, between the developing pi bond and those electron withdrawing substituents. So again, the answer is nothing more than that. And you can memorize that. It's usually what my students do, because I'm not going to ask you to write an essay about it or anything like that. It's just you need to know that the endo product is going to be the major product. And it's based off of those favorable interactions between the electron withdrawing substituents on the diene and the developing pi bond. Nothing more than that. So the endo transition state is lower in energy, and so the endo product forms faster, even though it is a little higher in energy. The product is, right? Why would the energy or product be higher in energy? It's because, like I said, these groups are closer to the bigger bridge, right? Whereas here they're closer to the smaller bridge. So the exo product is actually more stable, but again, it doesn't have this favorable interaction in the transition state. Well, what about regiochemistry, right? If you have a symmetrical diene like you do here, or if you had a symmetrical dienophile, well, then you don't have to worry about regiochemistry at all. You just slap some curved arrows on it like this. You draw the product that results, and you're done. Okay, maybe I could clean this arrow up a little bit. There you go. Doesn't matter. Same thing here. You draw some curved arrows, and there you go. You're done. Okay, hot dog, we have a wiener. But you have to consider regiochemistry when you have an unsymmetrical diene, like this one here, and an unsymmetrical dienophile. In that case, you get two regioisomeric products that could be formed. And you see here that one of them is major and one of them is minor. And you need to be able to predict why, or determine which one would be the major product. And there's a good reason for that. Okay? Now, the reason why is because we can look at the charge distribution over the diene and the dienophile. See with this methoxy group in this position? You can draw curved arrows that show a negative charge over here. What does that mean? That means that if we go back here, there is some partial negative charge here, right? Now, if you look at the dienophile, you can draw a resonance contributor that shows a positive charge on this carbon that's part of, that is part of the 1,2 system that's involved in the reaction. So you can draw a delta plus right here. Fix my delta a little bit, but you can draw a delta plus here. So what's going to happen is that the diene and the dienophile are going to arrange themselves or orient themselves so as to maximize the electrostatic interaction or attraction between the partial negative and partial positive charge. So you can see that they're not aligned in the right way here. I'd have to flip this around in order to get it to look more like this. So now I have the partial negative here aligned with the partial positive, right? Why? Because I'm maximizing the electrostatic forces, and it results in a lower energy transition state, and this produces the major product, and this product is going to be formed faster. And so you can see that you have to be able to draw those resonance contributors and have to be able to show where the partial positive and partial negative charges are in a diene and dienophile. Well, with that in mind, what's the best thing we can do now is to try some practice problems. It says predict the products for each of the following reactions. I'm going to go over this one a little bit quickly, and I don't mean rushing, but I mean I'm not going to go over it too slowly, because I think the best thing for us to do as a group would be to take a look at a couple of these, and then for us to pause the video and for you guys to try them yourselves, and then we'll come back and take a hard look at them. So if we look at C, the way that it's lined up, there's nothing wrong with it, but I find that students find it handy if you try to draw, or if you draw everything like this, and you see that you have, a trans like this, we have the carbonyl like this, and then we have the carbonyl like this. So that will usually help my students. Let me fix it up a little bit here. If you draw the molecules oriented in such a way so that you see the diene like this and the dienophile like that. Okay, so we're going to combine those molecules in a Diels-Alder reaction. I think we should draw the curved arrows. So we're going to form a sigma bond here. We're going to break this pi bond, and we're going to form a new sigma bond here. Then we're going to move that pi bond over there. And what's that going to give us? So don't have enough room here to draw everything, but we're going to end up with a 6-membered ring. Okay, that's going to look like this. We're going to have a pi bond here. Then we're going to have a bond coming up here and a bond here. But remember that since this alkene, the diene, is trans, what that means is that one of those what that means is that one of these groups is going to be pointing up, okay, like this, and the other one is going to be pointing down like that. So we're going to have our carbonyl here, and then we have the carbonyl here like that. So we're going to get this plus the enantiomer. All right, so that's what happens in the first one. Now in the second one, there's no cis or trans to worry about, is there? So let me move over to a blank space here, and we'll take a look at the next one. So I'll get past some of this stuff we did today. So this is 16.13D. I have my diene. I'm going to draw the dienophile like this. It's got a triple bond in it. We've got a carbonyl, a methyl, so that's called like a methyl ketone, right? Here and here. We're going to draw our curved arrows. We form a sigma bond. We break this pi bond, form another sigma bond, and then we form a pi bond. We're going to draw what we end up with, which is a 6-membered ring. Like that, we've got a pi bond here. We still have a pi bond here, and so these carbons are sp2 hybridized, so they're trigonal planar. There's no stereochemistry. There's no up or down to draw there. And there you have it, my friends. All right. I'm going to leave E and F for you to give a try to for next class. And I want to move on and try 16.17. So this is question 16.17, and we'll just try one or two. Let's see here. Let's try C. We start with cyclopentadiene as our diene, right? Plus this molecule. So now our dienophile has that electron withdrawing group. Since our diene is symmetrical, we don't have to worry about regiochemistry and drawing delta pluses and delta minuses. But I wanted to cover this one because now we're going to form a bicyclic product. Right, we're going to form a new sigma bond there, a new sigma bond here, and a pi bond like that. So it might take some practice to draw these bicyclic products. So you have the 5-membered ring, which is going to look something like this. And you have the 6-membered ring, which will look something like this. And then you have the endo, or you have this position going up, right? And then you have this position going down. So you could have the carbonyl going down, or we'll put, and you're going to have this compound as well. So I'll practice drawing my bicyclic structure like that. I'm going to have the aldehyde pointing up and the proton coming down like that. All right. Sorry, I'm mistaken. After I drew this, I was like, that's not right. You actually won't form this product, okay? You might form it in a small amount, but according to our textbook, you don't form any of that product. Okay, so you're only going to form this product where this group is pointing down. Why? Because it's the endo product, right? This is endo, but then you're also going to form the mirror image, right? So you'd also end up forming the enantiomer of it. So we'll put this plus the enantiomer like that. So what I recommend before our next class is, or before you watch the next video, is attempting questions 16.13 from the textbook, question 16.17, and question 16.18. So make sure to try those before you watch the next video or before our next class.